Okay, all of you got the link? Okay, come back fast, fast, fast. Sorry, there was a network issue. So all of you are back. Okay, we will wait for another 1 minute. Okay. Okay. So all of you are here. So that's where I was talking about how this is going to function. N and P type of semiconductors, how it's going to function. That's where there will be formation of NP junction. Okay? And that's why whenever there is a energy which is supplied, there is solar energy, whatever electron, excess electron is there, now it will be easily moving to here because of the positive hole. Right? So that's where conductivity will happen. There will be movement of electron from N type to P type. So there will be movement of electron. Due to that, there will be formation of electricity. All of you have understood? That is one of the application. Okay, where N and P type of semiconductors together it can be used. Fine. So this is how it's going to function. So due to the presence of positive hole, it will make easy for N-type semiconductors to move the electron to P-type due to the presence of the positive hole along with anode and cathode. That's why it is making much more faster movement of the electron. Okay? Fine? Now, before going to the next concept, Archit, what is that doubt you were asking? Because we have done with electric property, conductivity property. Now we are moving to the magnetic property. So before that, because if it is late, then it will be postponed to tomorrow. What is that doubt you wanted to ask? Okay. Sir, the location of tetrahedral watts and okay, Archit, when it comes to locating tetrahedral, from that's where we got that equation where now total number of atoms is equal to n, number of tetrahedral watts is equal to 2n, and number of octahedral watts is equal to n. So from that's where from locating the tetrahedral and octahedral watts we have deduced that particular, or we came to a conclusion for that particular equation. But when it comes to locating tetrahedral and octahedral watts, don't worry, it's not there for in your syllabus. In textbook it is there, but deducing that one, locating that one, it's not there. Explanation they have given in textbook, but no need to worry, it will not be asked for your exam. But you should remember about 2n and n. That one you should remember. That actually basically came from locating the tetrahedral and octahedral watts. That is one thing. That's why I have skipped that. Okay now? And another important one is for that, this is not enough. I have to use the YouTube video or something like that. So, okay, so that you can understand. Otherwise it will be difficult. I cannot draw the picture. Fine? For competitive exam also very less, rarely they have asked. I don't think CET, NEET and all they have asked. I will go through that. I will see some of the questions from previous years. Whatever it is required, we will have a discussion, that one only. Okay na? But I don't think for locating the tetrahedral and octahedral watts that will have such weightage. Fine? Problems they will ask. Like related to n and 2n, problems they have asked many times. But locating the tetrahedral and octahedral wards, NEET and CT, I don't think so. But JE, I will go through the questions and let you know whether they have asked. Fine? Okay. So in that case, we'll move to the next one, that is related to last part, that is related to magnetic property. That is related to magnetic property. Hagadre, when I am talking about magnetic properties, why we have to discuss, or why some of the elements they have the magnetic property, and one of the quantum number itself is magnetic quantum number, right? So which talks about spin of the electron, right? So now when I am talking about spin, means I am not talking spin quantum number, I am talking magnetic quantum number, which is related to electrons, how it is oriented and all. Sir, there are questions related to how many number of data inside the SCP and how many are outside. Okay. So in that case, we'll have a discussion about that one later. Fine? Archit, that's fine. But still we can write that one. But outside, yes, for that we have to go through that. I will explain it. Okay, na? So now when it comes to magnetic property, now when why a element will have the magnetic property? That is due to the charge of the electron. However, only charge of the electron is responsible? No. Because of the charge of the electron, and since they are not static, they will be spinning around their own axis and they will be revolving around the nucleus. Okay, na? Since they are spinning around their own axis and since they are revolving around the nucleus, it's like, for example, all of you will go to the temple, right? So in front of the God, whenever you will do like this, then you will rotate, you will do like this, na? This is nothing but spinning. You are rotating around your own axis, that is called as spinning. But when you are taking around the God, that's where it is called as revolving, right? So since electron is spinning, at the same time it is rotating around the nucleus, and since electrons are charged, they are having negative charge, so therefore they will have the magnetic property. Atoms will have the magnetic property. So that's where we have the different categories. So in that already we have discussed in first year, that is paramagnetism and diamagnetism. That's what we have discussed. Paramagnetism and diamagnetism. Now, one of the common feature, I am not telling it is universal, one of the common feature with respect to paramagnetism and diamagnetism here is, when it comes to paramagnetic elements, they should have unpaired electrons. They should have the unpaired electrons, at least one or more than one unpaired electron, minimum one should be there. But that is not universal, please remember. So that's where we have the unpaired electrons. Here there is no unpaired electrons, all are paired electrons, which is left over. Okay, there will not be any unpaired electrons. Fine. Sometimes we will be having a question. In that case, sir, if that is the scenario, why copper is diamagnetic? Copper normally considered as diamagnetic, not paramagnetic. Although outermost electron, if you take for copper, it will be 4s1. It will be 4s1. So that's where one electron is present in copper. Then why not copper is considered as, or why copper is not behaving as a paramagnetic element? Because when I am talking about paramagnetism, it's a property of an element where they will be having weak affinity towards the magnet. They will have the weak affinity towards the magnet. right? Yes, Amit. Cupric is paramagnetic, but not copper or cuprous, Cu plus. Fine. So why copper will not be having paramagnet? That's why I told. It is a general statement, but not universal. There should be presence of unpaired electron. That is fine. A general statement, but there are many exceptional cases. Fine. So, for example, copper only. Now, the reason is very simple. Although we have one unpaired electron in copper, that may not be enough to show the magnetic property. Got my point? Even nuclear force is also going to count. Even nuclear force is also going to count. So that's where in the general way we can tell, it's not wrong. In general way we can tell that paramagnetism will shown by those elements which will have unpaired electrons. Absolutely correct. But in case of the copper, since that unpaired electron is present in S subshell, that is one thing. And all of us we know that S subshell is feeling more nuclear force compared to any other subshell. That is one point. And since there is only one unpaired electron, that might be the reason why magnetic property of the copper might not be observable. So therefore in general copper will be considered as diamagnetic. But if I take oxygen, based on molecular orbital theory only we can tell that oxygen is having unpaired electron. So oxygen, then cupric ion, all of them they can be an example for paramagnetic elements. All of them they can be an example for paramagnetic element. That is oxygen, cupric ion, they are all, even Fe plus 3, they are all example, Fe plus 2, they are all example for paramagnetism. Okay. Now when it comes to diamagnetic, for diamagnetic we have examples which are those elements which will be having paired electrons. Okay. There is no question of unpaired electrons, non-conductors normally. So that's where we have pure water or NaCl crystal. They can be examples here. Pure water or NaCl. I am taking from your textbook only. So water, NaCl, they are all some of the examples for diamagnetic compounds. All of you have understood? Fine. So here we are restricting ourselves to electrons belongs to particular energy level. That is, electrons naturally belongs to outermost energy level. Here we are focusing on that when it comes to paramagnetic and diamagnetic. But we have some of the concept where it is called as ferromagnetism. Then it is called as ferromagnetism. Even on this they will ask, important. So ferromagnetism, then antiferromagnetism, antiferromagnetism, then ferrimagnetism, then ferrimagnetism. Now ferromagnetism, all this concept, it is related to the total solid. We are not focusing on one particular atom. We are focusing on a total solids. Okay. Now their domains, how they are exactly arranged. One point here you should understand here is why in paired condition there is no magnetic property, especially when it comes to diamagnetism. They will be slightly repelled by the magnetic field. They will not be attracted. They will be repelled by the magnetic field. So that is because of the opposite spin of the electrons, which is going to cancel each other's property due to the presence of opposite spinning electrons, which will be cancelling each other's property. That's what we can observe in the diamagnetism. That's what I told. When it comes to paramagnetism and diamagnetism, we are focusing on one particular element. But when I am talking about ferromagnetism, antiferromagnetism and ferrimagnetism, we are talking about the total structure. Okay? Now, when it comes to ferromagnetism, if I take a solid, That's how the individual domains will be arranged in one direction. Whatever their spinning action is there, it will be in one direction. Okay? But when it comes to antiferromagnetism, in this case, equal number of opposite spins will be there. Domains, I am talking about domains, not individual atoms. So atoms present in this domain, atoms present in this domain, like that. I am talking about the domain. So better I will make it as a circle. Okay? So that's where when it comes to ferromagnetism, this is related to antiferro because they will cancel. Each domain will cancel another domain like paired electrons. Okay? But when it comes to ferrimagnetism, there will be regular arrangement. Some of them will be like this. Okay? And some of them will be like this. Or they are not equal and opposite. Some of them in one direction, few of them in opposite direction. Then they are not equal and opposite. That's where we have the ferrimagnetism. All of you have understood? Fine? Amit, random is related to, okay, I can tell, yes, ferrimagnetism. Okay? So that's where we have the ferromagnetism, antiferromagnetism and ferrimagnetism. Fine? Now, when it comes to ferromagnetism, they have the strong affinity. They have the strong affinity towards the magnetic field. Even they can be converted into a magnet. If you provide a suitable condition, they can be converted into a magnet. That's where we have the ferromagnetism. Like nickel, iron, they all belongs to this category. So nickel, iron, they all belongs to ferromagnetic elements. So which can be converted into magnet, permanent magnet. They can be converted into permanent magnet. Fine? But at one particular point, which is called as Curie point, at which iron can be converted into paramagnetic. That might be there in your physics. So that is called as Curie point, right? So where iron can be converted into paramagnetic element. Fine? That is a temperature. That is nothing but I am talking about temperature where it will be converted into paramagnetic element. So which element is actually ferromagnetic. But now at that particular temperature, it will be showing the paramagnetism. That temperature is called as Curie point. If I am right, 778 or 68, 768 degrees Celsius. Okay, anyway, this is 768 degree Celsius. Yes, if I am right. So that's where at that particular temperature, iron, which is actually a ferromagnetic type of element, it can behave as a paramagnet. Now we have antiferromagnetism where manganese oxide can be the example. We can show the antiferromagnetism, which will show the antiferromagnetism. All of you have understood? Fine. So in this case we have ferrimagnetism, we have case magnetite. We have the example as magnetite. Magnetite can be the example which we have discussed. What is magnetite? Iron ore, but what is the formula? Formula is Fe3O4. Fe3O4. Magnetite can be the examples. All of you have understood? That's where we have the ferrimagnetism. So in case of the ferrimagnetism, they have the slight affinity towards the magnet. Just like paramagnetism only, they have the slight affinity towards the magnet. But in paramagnetism, we are focusing on element. But in ferrimagnetism, we are focusing on domains of the solid structure. Fine? So that's where we have the three properties. You should be remembering this. All of you have understood? Any doubts? Even ferrites also there. Yeah, ferrites. Okay. So have a look on that. We are in the last part, no need to worry. So even ferrites where XFe2O4, where X can be zinc, manganese, etc. Okay. Now whether it's clear? You can see the board last 2 minutes. Now whether you can see? Okay. So I was telling even ferrites, you can remember the examples. Okay. So where X can be zinc, manganese, even magnesium, they all belongs to ferrites. General formula is XFe2O4, where X can be some of the other metals, transition metals. Okay. So that's where we have the ferromagnetism, antiferromagnetism and ferrimagnetism. So when it comes to definition, ferrimagnetism and paramagnetism, they will be overlapping. But when I am talking about paramagnetism, I will be talking about spinning of the electrons. Okay? But here, I will be talking about the domain structure. I will be talking about arrangement of the domains in a solid structure. So that's where the difference between ferrimagnetism and paramagnetism. Fine? So any doubts? So by this solid state we have done. We are done with the solid state. Any doubts? And tomorrow we are going to start with the organic chemistry, that is amines. Tomorrow we are going to start with the organic chemistry, that is amines. But any doubts in this? And Archit, with related to that we will see. That is related to location, whether I can get the video for that. Fine, because by using only blackboard it may not be it will be difficult for me to draw the picture, and about that it might be difficult for me to explain it to you also by using the simple blackboard. Fine. Okay, in that case, take care. Thank you.